Recording started. So the agenda is on plane and surface intervals. And I start out by looking at an axis parallel rectangle. And this is a kind of repetition of what we did last Wednesday, but I do this in order to introduce this parametrized plane field. And then let me write it. A parametrized surface. And here I'll do one example, and that is a cylindrical surface. And then I'll talk about the mass midpoint. And then I'll end up by introducing the project work. So, we're given a mass function. And this is a function of two variables. And it could be the density, but it could also be the density times the thickness of a plate, for instance. But this is a mass distribution function of two variables. And we also have an axis parallel rectangle. Okay. And how does that look? I draw here the new space, and let this be the axis parallel rectangle, and in the u direction it goes from A to B, and in the v direction it goes from C to D. And the question could be, given a mass distribution over this rectangle here, what does this rectangle weigh? What's the weight of this rectangle? And we're going to find out what that is. What it will do is that I will partition this interval here in, I write here, partition in segments of length delta u. And similarly, I partition the interval CD in length dB. So let me give you an example of this. So this is then your dB here, this distance. velocity. And then I partition similarly. This in segments of equal lengths. And what I then do is that I take these corner points and I name them. This one here is U1, V1. This here is U2, V2, and so forth. This one here is U1, V2, and this is U2, V2, and so forth. All the corner points here are named in this way. And what I can do then is that I can say, if I look at this, or at this stretch here, I better take these out. This stretch here. And then I want to compute, say, the mass of this section here. What I do is that I take the mass function in that point, and then I multiply by the area, and then I add the mass of this by taking the mass function at that point and multiply it by the area. So let's say that. So M will be the sum of all these elements, and that will be from, say you have n segments, and here you have m segments. So if I take this one, I'll take the left, the value here. That will be f of u I v1. This is for this first line here. And then I multiply by the area of each of these small rectangles here. So this will, in a sense, give me an approximation of the mass of this first strip here. If I then add the second strip, I get E, then I get F of UI, but then I should have B2, because now I've moved up here and then I have all these values here. And this will, of course, continue until I have covered all the strips in the V direction. Now, you see, I could then write this as a double sum, because I'm summing over all the V's here. So that will be J equal to 1 to M. You have M strips here. And then I equals, and then delta U, delta V. We saw the last time that when we did this, or we made a definition, that if we took the limit of this double sum as n goes towards infinity, and as m goes towards infinity, then this was the definition of the integral. So I take here the limit value, as n goes to infinity, m goes to infinity. And then I end up by having this integral, the integral from c to d, the integral from a to b of this function, du. So this is the double integral. But how do you actually calculate this double integral? You see, if you take the sum here, then you could write this as j equal to 1 to m, and then you have a parenthesis where you have the sum from I equal to 1 to n of and then I can put this outside. So what you have here is just a left sum of this function for a given j value, but this is the definition of a single integral with respect to u. So I could write this as the integral from c to d, and then the integral from a to b. So the way to calculate this, if you're going to use integrals, is that you calculate the innermost integral first. And this is an ordinary, you're keeping b constant. This is an ordinary integral, as you know from high school. And when you have done that, then you have the result is a function that depends on v. And then you have to make the other integration, which is again a single integral. So that's the way to compute it. Let me take an example. And I think we did that example last week, so I'll do it quickly. It's 3u squared v, and I have my rectangle, which is from 0 to 2 and from 0 to 3. And I want to compute the mass of this rectangle here. That is, I integrate from 0 to 2 and from 0 to 3. And we did that the last time by taking the limit of the double sum. And I did that in Maple. And I found that the result was 54. So let's see if we can do this by ordinary integration. I write this as the integral from 0 to 2, and then the innermost integral from 0 to 3 of this function. All right, u dv. So firstly, I have to keep v constant, and then I have to integrate with respect to u. So I have still this. So I have to find an indefinite integral of this integral. We've done that a couple of times, so I just write that this is u cubed times v. If you differentiate this one, take the derivative of this one, you get 3u squared times v, and this is this one. And you have to take it between the limits 0 and 3. If you put in 3, you get 27, and you get nothing from the lower limit here, so you get 27, and then and this is a constant, I can put it outside the integration sign, so we have the integral from 0 to 2 of v. So this will be 27, and then the integral of this one is 1/2 v squared, and you take it from 0 to 2. Again, nothing from the lower limit. From the upper limit, you get 2 squared, that is 4 divided by 2, that is 2, that is 54. And this is exactly the same value as the limit of the double sum, which we did the last time. And this is the essence of what we're going to learn about integration. That is to break it down into ordinary single integrals. And then you can use all your skills in partial integration and the method of substitution and so forth in order to calculate these integrals. Or you can use matrix. Yeah. Now, I'm going to extend this to and I do it by giving an example now. I'm going to extend it to a situation where you do not have a axis parallel rectangle. What do you do then? It's still a plane integral, but your field is not axis parallel. I'm looking at this function. So this is my mass density. My field is this set. X is bounded by -1 and 1. Right, and Y is bounded by this one and 1 minus x squared. Now, a good approach in order to understand this is to simply draw the field and see. Well, I should first write what am I going to do? I'm going to determine a parametric representation of V. In what follows, I will use this abbreviation, parametric representation of V, and this is termed V with an index R, where R is the coordinate or the vector of the parametric representation. And when I've done that, I'll compute the integral over this area of my mass density like this. So what does this mean? Let me first draw the field. That is, I want to draw B. So I have here X and Y. When I look at it, I can see that X is between -1 and 1. So x is here, but what about y? You can see y is larger than 0 or equal to 0, but it's less than this one. This depends on x. So a good thing is to draw this boundary for y. So you see equality sign, and then you can see it's a parabola, and it has a minus sign, so it's bending downwards. And then it is moved from the normal position 1 up. So so this will be the vertex of the parabola here, and it's pointing downwards. So it looks something like this. So this is the area, this is B. And this is, I'm going to find the mass of this, this area here. In order to do so, I need a parametric representation of this field. And how do I do this? Well, the first thing I would like you to understand is how you parameterize the line segment. That is, if you have a segment from P to Q, like this, how is this parameterized? How do you describe all the points on that? So I want a parametric representation for the line segment PQ. And the thing here is that you start by the starting point, and then you take this direction vector here, and then you multiply by your parameter. And the parameter belongs to this interval. You see, if t is equal to 0, there's nothing to add, so you are in P. This is this point here. If t is equal to 1, then you are at this point. If t is 1/2, you are at the midpoint, and so forth. In this way, you can reach any point on this line. So the way to use this here is that I'm going to use a vertical line here. This point here is u considered. That is, I used x as one parameter. I need two parameters in order to fix this this relation here. So this is this point, and then in order to follow this one, I need the directional vector from this point to this point. This point up here has the coordinates u, 1 minus u squared. So I'm looking for my function, our function, and I have the starting point, which is u kind of 0, and then I have my parameter, now I call it v. This is common practice. I'm going to write it this way. V. And then I need this directional vector here. You can see it's a vertical vector. So the second, or you see the first coordinate for this vector here is 0. It's vertical. The second coordinate is 1 minus u squared minus 0. That is 1 minus u squared. And then I can write it together. I get from the first coordinate, I get u. From the second coordinate, I get v times 1 minus u squared. And then I have to consider the intervals. Of course, I know from the way I have constructed this one that v is running from 0 to 1. But you see here, I could have drawn it here, this line. I still have these two endpoints, and this will then be a parametrization of this line here. And if I choose u to go from -1 to 1, then I cover all lines in this area. And this way I cover the whole so this is the parametric representation. Now, so I've done this. Now I'm going to find this integral. And in order to do so, I'll just write down the formula. It's the integral. What I'm going to do now is that I'm going to unfold this symbol for a plane integral. So it is this double integral from C to B and from A to B. And then I have my function of x and y, that is the mass density. But instead of x and y, I write my parametric representation. So now this composite function is a function of the two parameters u and v. But then I have to multiply with the Jacobi function. And I just write here what the Jacobi function is for a plane integral. It's the numerical value of the determinant of this matrix where you have the derivative of the parametric representation with respect to u as the first column, and as the second column you have the derivative with respect to v. So what I'm going to do now is that I'm going to calculate this integral as it stands here, and then after a small break, I will tell you why it works and why it looks like this. I have here that you see my mass density is x squared, and x is in the parametric representation equal to u. So this is simply u squared. Now I need this determinant. So I need to differentiate my parametric representation with respect to u. I get for the first it's u, so it's a 1. For the second, I get minus 2vu. This was the first column. The second column I have to differentiate with respect to v. I get a 0, and then I get 1 minus u squared. So, and this determinant is this times this, and this is 0, so no contribution. So it'll be 1 minus u squared. And this means that the Jacobi function is equal, I should say, of u is equal to 1 minus u squared, because u is between minus 1 and 1, so this is not negative, so I can get rid of these absolute value signs or numerical value signs. So now I can write down my double integral here. So it will be the integral from 0 to 1, that's the v parameter, and the u parameter is from minus 1 to 1. And then I have the mass density, which is u squared, and then I have to multiply by the Jacobian, and then du dv. The innermost integral is, I could multiply this out, I get for the integral, that is u squared minus u fourth. So the indefinite integral of this one is u cubed over 3, and this one it's u to the power of 5 divided by 5. And you should take this between the limits minus 1 and 1. And then afterwards you should integrate this with respect to v from 0 to 1. Now, if I put in the upper limit, I get 1/3 minus 1/5, and that is 2 divided by 15, if you put it on a common denominator. And then you put in the lower limit, you get the same numerical value, and you should add it because this gives you, when you put it in, you get minus 1/3, but it's the lower limit, so you have to subtract it. So all in all, you get the integral from 0 to 1 of 4 divided by 15 dv, and this means that the integral is 4 divided by 15 times v, and it is between the limits 0 and 1, so the result is 4 divided by 15. Let's take a break until 10:45.